So right behind me you see our empty canvas where we have nothing, so we pushed everything in our lab back. Maybe you saw this on Twitter the other day, that we had it here full, with the full team actually working in the lab. However, now we had to empty everything because today the glove boxes will come. They will arrive in a few hours, so 2 to 3 hours, and we'll place them here, lift them through the wall. And this is going to be a glove box system. You'll see it in a few seconds, probably in this video, that will stretch all the way to the back. So super excited, and stay tuned for our big delivery today. So you might be wondering, why the heck did they order such a gigantic glove box? So you might be familiar with some of those glove boxes where you have essentially 4 arms, so about 2 people can work in one glove box. And why the heck is our glove box so gigantic? So one reason is in fact that we will place 2 large SCARA robots. So these are robots that can essentially move in the XY plane and in height. They can't really rotate inside these glove boxes to ensure an efficient sample transfer in between different measurement setups. So we have the scanning droplet cells, we have certain high throughput spectroscopy units, and we want to ensure just a very efficient sample transfer in between. Plus, these glove boxes actually became so big that we started to have problems to actually reach all the way into the glove box with our hands. Another reason is some of those things are pretty high and actually require a perfectly dust-free environment. This is mostly true for the scanning droplet cells. Imagine you have a scanning droplet cell area that is about 1 millimeter in diameter, and you just happen to have some, little speck of dust that is on your substrate. Now, if you have that and you would do the measurement, your measurement would turn out to be, wrong. So what we do actually in this glove box, and this is why they're a little higher than usual, is we actually have a laminar flow system that pushes down the, well, not air, but the nitrogen inside these glove boxes, and really ensures that we essentially have a clean room plus a glove box. I just briefly said it, we are actually not operating in argon like most battery chemists do this. We operate in nitrogen. Simple reason is that if we were to do this in nitrogen, some of our electronics actually are known to not work properly. That's mostly because argon has a little bit different arcing property than you have in air or in nitrogen. So we actually fill this whole thing with nitrogen, but it's perfectly dry, so it has no water or oxygen inside of it. The reason for that is if you're working with some of those special chemicals that are inside batteries, so lithium hexafluorophosphate or sodium hexafluorophosphate, they actually tend to form hydrofluoric acid, which is a really dangerous chemical. And you want to just simply avoid this, and the simple way to avoid this is to have 0 water inside your atmosphere. And this is another reason why we have these special glove boxes. So the bigger picture is, where you're standing right now with the camera is where we will have our synthesis system. In a battery electrochemistry, you really have the problem that you can't work in ambient atmosphere, meaning in air or in a, let's say, moist environment. So this is why we have these large glove boxes. Inside these large glove boxes, there are different measurement setups that can characterize what we have synthesized in our synthesis chamber. Now, this characterization is tightly integrated. That means we can do electrochemistry and can automatically transfer the sample from the electrochemical characterization station to a spectroscopic characterization station with a simple SCARA robot. We do this in 2 different compartments, so we call this box A and box B, which has again the size of 4 normal glove boxes. And the simple reason is, in one we do more of the wet chemistry focused characterization and handling of wet chemicals, and in the other glove box we mostly do this with dry materials. So we have that, plus we actually have this entire line set up in such a way that we have the synthesis, again where you're standing, the characterization in the middle, and the really high-end characterization all the way at the end. And there's actually a XPS, or an X-ray photoelectron spectroscopy machine, will be delivered hopefully in September. And you actually want to, or you need to ensure that if you transfer a sample from here all the way to the back, you actually cannot expose it ever to atmosphere. So this is one of the reasons why we actually have this continuous going from here all the way back. You need to do this to, well, first of all, have really high fidelity data, but you also need to do this in such a large compartment to actually be able to integrate different measurement setups without having people to run through the lab and potentially contaminate their surfaces or the battery materials. So this is a pretty large piece of equipment. Why do we actually do this? So we do this for a couple of third-party funded projects. One of them is, of course, the POLiS Cluster of Excellence located here in Ulm and Karlsruhe. But we have another really big project, and this is BigMap. So in BigMap, the European battery community comes together and tries to really form a platform that spans the entire European continent to really advance the battery chemistry by a lot. So our aim is actually to accelerate how we do battery chemistry by a factor of 5 to 10, meaning we no longer need 40 or maybe even 60 years actually from discovery of a material to real commercialization, but to actually shorten this to about 4 to 10 years. Which might sound still like a long time, but you want to have a safe battery in your home or in your car. So one of the big ideas that we have here is we want to enable scientists from all over Europe, but even the entire globe, to be able to interact with our machines through the internet and actually have like a distributed laboratory that anybody in the world can practically access, and where we can really do measurements and synthesis for other groups. Plus, we want to have the capabilities here that we can actually even operate machines in other labs. In fact, we're doing this partially already with a lab down the street at ZSW, where our machine learning algorithms that actually running down in the basement on some servers that we have placed there, they are running the machines down the street, and we essentially want to enable other scientists to do exactly the same thing, that they can actually use their algorithms, their optimizers, and run our machines here in our lab.